In section 10.3, I'm going to do some numerical examples featuring objects undergoing circular motion. In circular motion problems, it's very common to be asked to calculate some minimum or maximum value. And there's three different situations. The first is when the centripetal force is provided by static friction. An example of this is a car rounding a curve. You need to remember that static friction has some maximum value, and that if that maximum value is exceeded, well, then the static friction will turn into kinetic friction as the object will then start to skid or slide across the surface. Some problems involve a object undergoing circular motion due to a centripetal force provided by normal force, like an object in a loop-de-loop. You need to remember that the normal force is allowed to be zero, but it can't be negative. Normal forces can only push away from the surface, they can't pull. And therefore, the min or max condition is going to happen when the normal force drops to zero. If the normal force required is some negative value, then the object will no longer move in a circle. And sometimes the centripetal force is provided by tension. Now, tension is allowed to be zero, but it's not allowed to be negative, just like normal force. And so then the min or max condition will occur when the tension drops to zero. You also might see a min-max problem involving tension where they give you the maximum value for tension for a given string or a cable, where if that tension force is exceeded, then the cable or the string snaps, and then obviously that tension force would be at a maximum. Okay, so let's look at this one. Here we have a 90-kilogram skateboarder riding into a valley with a radius of curvature of 5 meters. Now that's a phrase that you're going to see a bunch. Radius of curvature. That just refers to the circular path that the object is moving in, but it might not be a complete circle. So that's saying if the circular path was a complete circle, that radius would be 5 meters. The skateboarder is going to reach the bottom with a speed of 10 meters per second. We're to neglect drag, and we want to find the net centripetal force and the normal force acting on the skater. So the skater will have his weight force acting down. There will be a normal force acting up, and it's important to note that the centripetal direction towards the center of the circle is going to be up, and therefore the net centripetal force is also up. Now that net centripetal force must equal the skater's mass times the centripetal acceleration that the skater experiences. And the centripetal acceleration, we have an equation for it. It's speed squared divided by radius. And when we plug in our numbers, the mass is 90. The speed is 10. Don't forget to square it. And the radius is 5. And when we crunch the numbers, we get 1,800 newtons. So now that we know the value of the net centripetal force, we can use that to work out what force the ground has to exert on the skateboarder, the normal force. The net centripetal force will equal the normal force minus the weight. I know the value of the net centripetal force is 1,800 newtons. The normal force is what I'm solving for. And the weight force is going to be the object's mass, which is 90 kilograms, multiplied by g. We use a value of 10 for g. So the skateboarder's weight is 900 newtons. And so the normal force acting on the skateboarder is going to be 2,700 newtons. And just to point out that this value, this is how heavy the skateboarder feels. Anybody that's ever driven in a car that goes through the bottom of a hill knows you kind of feel a little bit heavier than you normally do. And that's because the normal force required to have you move in a circular path has to be greater than your weight. So you feel a little bit heavier than you normally do. In this example, we have a car that's driving over a hill that has a radius of curvature of 12 meters, and it's moving with a speed of 8 meters per second. We want to know how heavy the car's 80 kilogram driver is. So for part A, this is really straightforward. Weight is mass times G. We have a mass of 80 kilograms. G has a value of 10. And our 80 kilogram driver weighs 800 newtons. Now, how heavy does the driver feel? In this case, they're asking us to calculate the value of the normal force. So we can draw a quick free body diagram. The weight force acts down, the normal force acts up, and the car and driver are in circular motion. Therefore, we need to account for the centripetal direction, which in this case is down. And so the net centripetal force has to be m times the centripetal acceleration. And we can add up the forces to get the net centripetal force. In this case, it'll be the weight minus the normal force. And if I solve this equation for the normal force, you end up getting weight minus MAC. The fact that you are subtracting some value from your weight, if you're in the frame of reference of the car that is undergoing a circular motion, it's non-inertial. And so this is that centrifugal effect that I talked about in section 10.1. It feels like there's a force pushing you upwards, but there's no force pushing you upwards. It's really just a consequence of you being in a rotating reference frame. The centripetal acceleration is speed squared divided by radius. And I have all of these values. The weight is 800 newtons. The mass is 80 kilograms. The speed is given as 8. Don't forget to square it. And the radius is given as 12. When you crunch the numbers, you end up getting 373 newtons. And so this driver is going to feel lighter than normal, and that's because the driver feels as though there's an outwards centrifugal effect sort of pulling them up, seeming like they are experiencing a force that reduces their weight. Okay, so for part C, what is the maximum speed that the car can pass over the hill? So for part C, I want to look at this equation right here. So weight minus the normal force has to equal MAC. Now, the faster the object goes, the greater the value of AC. We require a greater centripetal force the faster the car goes over the hill. And so how can we reduce the left-hand side, or how can we increase the right-hand side? Well, the only way we can increase the right-hand side is to reduce the normal force. And so we'll end up getting our maximum speed when the normal force drops to 0. And the weight force is m times g. The centripetal acceleration is v squared over r. This is a interesting little result. Since there's a mass on either side, the mass cancels out. That's why when two people riding in the same car, even if they have different masses, they have the same maximum speed going over the same hill. The maximum speed does not depend on the mass of the rider or the object. The car doesn't has the same maximum speed. You end up getting the square root of g times r. The radius is given as 12. And when you crunch these numbers, you end up getting a value of 10.95 meters per second. Now, in part D, what's going to happen if the driver passes over the hill at 11 meters per second? Well, 11 meters per second is greater than that maximum speed that we just worked out. And if the maximum speed for maintaining circular motion is exceeded, well, then we won't have circular motion anymore. In that case, we're going to have some other kind of motion. And in this case, the car is going to lose contact with the road, and that means that it's going to be in free fall, and the car and the driver are going to experience free fall motion. Projectile motion. They'll move in a parabolic path until they contact the ground. Okay, and in our last example, we have an 800-kilogram car rounding a curve with a radius of 280 meters. We're given the coefficient of static friction between the wheels and the road as 0.4. We're to neglect drag and rolling friction impeding the car's motion. And we want to figure out the magnitude of the friction force if the car is traveling at 20 meters per second. So we'll start out by drawing a free body diagram showing the forces acting on the car. We've got the weight force acting down, the normal force from the road acting up, and we have a static friction force that provides the centripetal force necessary for the car to move in a circle. And that same force would look like this from a top-down view. And I'll slide everything over so that I have a little bit more room to work. And when we look at finding the static friction force, we need to note that the static friction force is what will provide that net centripetal force to make the car move in a circle. And so for the car to move in a circle, this condition must be met. The net centripetal force is the static friction force. There's no other forces acting in the centripetal direction. I can replace the centripetal acceleration with speed squared divided by radius. And I can fill all the variables in. I know the mass is 800. I know the speed is 20. And we're given that the radius is 280 meters. When we crunch the numbers, the static friction force is 1,143 newtons. But when we look at this equation here, we'll note that when the speed increases, we're going to need a greater frictional force to keep our car moving in a circle. And I'll recopy that equation one more time. We should note that static friction has a maximum value. Static friction is not allowed to exceed the coefficient of static friction mu s times the normal force. Now, when the left-hand side of this equation is a maximum, when mv squared over r is a maximum due to the speed being its maximum value, this is going to equal mu s times the normal force. Well, the car does not move in the y direction, so the normal force has to equal the weight. Well, the weight is equal to m times g. So we see again that there's a mass on the left and right-hand sides. The mass cancels out. That's important for engineers designing roads because you don't make separate roads for cars with different masses. A big semi-truck can round the same curve that a really small car could, provided that they had roughly the same mu s between the tires and the road. And if we rearrange this equation for V max, we'll need to multiply both sides by r, and then we'll need to take the square root. And I can fill in all my values. Mu s was given as 0.4. G is 10. R is 280 meters. Don't forget to take the square root. And when we crunch the numbers, we get 33.5 meters per second, which notice is larger than the 20 meters per second in part A. The maximum speed that any car can round this same curve of a radius 280 with these type of tires is 33.5 meters per second.